Hello everyone, कैसे हो? Welcome back to another video. This is your friend Subham over here, and welcome to the YouTube channel Curiosity Corner. Before I jump into the video, let me tell you something interesting. Basically, it's the part of the video. So, Indicon 2024 was held at IIT KGP, and from 2019 to 21st of December, and my paper got shortlisted for that. Shortlist basically you submit the paper, and then my paper got accepted, and I presented over there. Now, the fun thing is, it was a really good conference. I enjoyed a lot, got to learn a lot, and I'm going to share all those stuff in the series of videos. This is first of the video of the series, and I do not have the camera as of now because I am at my hometown. So when I will be back in Bangalore, I will be doing a video. Having me on the camera as well, and I'm going to talk more about it. But to start with, it was a really good conference held at a very prestigious institute, and the best part was again the learnings that I got from it. And again, to present your work in such conference gives you a boost basically. And I'll going to show you the presentation which I showed over there, presented basically, and then in the next upcoming videos we are going to talk more about it and why this kind of work is very important, because we are going to talk about that as well. So going into it, I posted this on LinkedIn basically, and then people were talking about it, to do a video on YouTube channel as well. So for that purpose, I'm doing it because many of my friends suggested me, motivated me, to be honest, to do this, right? So let me show you the notification of decision, and I was very happy to see like I'm doing something. The work basically is going into such a good conference. The problem with these conferences is, not the problem, but the good thing is the rejection ratio is very high, meaning as far as I'm aware, in the world top conferences of the world, it's less than 1%. Here I believe it's less than 5%, meaning let's say there are 100 papers, 95 will get rejected, and even less than 5 is going to get accepted. So the quality of work that comes out from these conferences is very good. And the title of the paper was recursive additive attention based CNN model for plant disease detection. So this is the domain wherein I have been curious looking into it from a very long time. Long time as in from the college days in 2018 when I was first introduced to it. And if you know me, if you know the channel, you know that I particularly work as in like, spend out of the office hours on this kind of activities, primarily doing research work, doing curiosity. The curiosity stuff in me makes me go through all this stuff, because it keeps me updated with the latest trends that's happening in the world. And we are in the age of data, Gen AI, LLMs, and all those stuff. So anyways, it keeps me maybe a step ahead of the normal people that you are going to talk about. Why I'm going to talk about that, why that is, I'll show you quickly. Basically, let's go ahead and see the presentation. This is the presentation that I have. Let me quickly go into this mode. Yeah, right. And the best part is, you cannot publish an article in this kind of conferences without your paper being mathematically sound. Obviously you have to be mathematically sound with the work that you are doing. You should have a very good understanding of whatever you are doing. Only then you will be able to come up with work that gets published in top tier conferences of India and around the world. It's not just some random conference wherein you just put a paper and any random work, any transfer learning work that you do and it gets accepted. No, you have to come up with your own architecture. Not just your architecture, but you have to mathematically prove what is, mathematically you have to show that how your work is better as compared, with the existing works, what you have done which is better than the existing work. So we are going to talk about that in the presentation going forward. And this is just one lecture, one video I'm recording. I will be doing a series of videos. So let's cover the basic topic, and plant disease detection, recursive additive attention mechanism based CNN model for plant disease detection, right? So I have been following this plant disease detection area for 3-4 years of time. And what I've seen is people, with the advent of vision transformers, if you know, vision transformers are vision transformers are basically an approach through which you can utilize attention mechanisms in the image processing domain, because attention mechanisms were ideally developed for the NLP domain. If you know chat gpts, llms and all those stuff, if you know, I mean, if you will dive deep into it, you will know the core of all the LLMs, Gen AIs, I mean, that exist today, not Gen AI, but LLM, yeah, Gen AI also. Just remove the GANs from there. Attention mechanism is the core of it, right? And there are different kind of attention mechanisms. So additive is just one of them. We have dot, I mean, you have scale, I mean, dot, I mean, there are several mechanisms like multi-head attention mechanism, you have self attention mechanism, you have dot attention mechanism, and there are few more to, I mean, the ones which came out like. So mine is recursive additive attention mechanism for plant disease detection. So let's jump into it and understand more mathematically what is it that has been done in this. I mean, and don't just say it's additive attention applied recursively. No, you have to be a very, I mean, you have to what do you say, present your work mathematically in the paper, as well as you have to prove your point that the work that you are doing or you have done is actually coming up with some good results. Now going ahead, introduction, I'm not going to talk more about it, just very introduction, like, you know, about agriculture domain, what hybrid plant varieties are there, variety of crops around the world, and then with the advent of time new diseases are coming in, so we need to be, and we have the data coming in from farms with the IoT sensors, and with a lot of stuff coming in, data is coming in a lot of the plant images of the leaves, so we can utilize image processing to get a suggestion of the disease. And this is one more thing I want to say, we always develop something to suggest people and not as a final what do you say, decision. We never make a decision to say, okay, what, this leaf has disease X. No, we always suggest. So I mean, it comes with a probability in fact, so that adds to it. Now going ahead with the paper, let's go to the related works that has been done. Anyways, I was talking about VITs. So VITs, or the vision transformers, utilizing the multi-head attention mechanisms, have been utilized for plant disease detection as well. And then there are not just VITs, just as CNNs were very much prevailing, and they're still prevailing right now. We had lightweight models of the CNNs, we had transfer learning approaches with which you can fine tune a model on your own data set with a very good result, but then when it comes to real scenarios it fails, right? And I mean, that is one of the disadvantage of, what do you say, a transfer learning approach. So you get a good accuracy F1 score, but then you end up I mean, with a, what do you say, on the real scenarios it just fails. So new architectures come in, people develop new architectures, new ways for image classification, and my work is primarily focused around image classification, plant disease classification of a leaf image, classifying what disease the current leaf has, right? And then a lot of lightweight and mobile friendly VITs and CNN models were also developed. I mean, talking about CNN, we had models like SSD for object detection, and for image classification we have mobile nets. So I mean, mobile nets is also there for I mean, object detection as well, but for the lightweight models we use them, I mean, for both the cases, right? So these are some of the related works that have been done in the domain. And then obviously the latest work that has been done in this is revolving mostly around VITs, some around GANs as well. I'll tell you why GANs, and I will tell you why GANs are being utilized for plant disease detection as well, because that is itself a problem. Now after doing a survey of the related works, after doing what do you say, analysis of the related works, we come to some problems, some problem statements basically, and that is what we try to, you know, solve. We try to what do you say, look into, and then come up with an architecture or an approach that solves the problem. And going into it, the problem statement states like, okay, we have a lot of images, but the images lack variability, meaning there are a lot of lightning angles. I mean, the images do, I mean, the count of the images is very low. When you say a deep learning model you want to train with, you have to have thousands of, I mean, millions of images. I mean, only then the model is going to be more robust. But in reality, for plant disease we have very few data sets, just 2 or 3. I know one is the plant village data set by SP Mohanty. So that is a very famous data set for plant disease detection. People have been using it for a very long time. And these labeled data sets are the ones which have, I mean, 40,000 images. But if you take, there are 38 categories, and then that boils it down to 7 to 800, 8.5k, 8 to 850 images per category which is not sufficient if you know for training model or architecture over your data set, I mean over this data set, it won't be sufficient. So for that there is a lack of data set, first thing. Secondly, the images are not having variations in the backgrounds, meaning you take an image of a leaf, the moment you bring it in reality to a farm, you will see you won't have the same background, and those background stuff acts as a noise, and then that noise becomes a big problem for the models, because even the accuracy drops. When the accuracy will drop, you won't be getting correct predictions of the model. Basically the generalization gets reduced. I mean, that's what is the first problem that I have been and we have been seeing. And GANs came into picture to solve this problem, because with GANs you can generate images with different backgrounds. So GAN was there to solve this problem. But anyways, there are certain other ways you can look at it. Augmentation is one such. GAN falls into that category as well, but it's a separate topic of discussion. We'll discuss about that as well going forward. And don't forget to put your comments in the video. What do you want me to elaborate more on, because in the upcoming videos we are going to talk more about this in detail, and going forward more videos are going to drop on the channel as and when I get time. So next problem statement was the limited feature relevance, meaning the same thing like if you look at a plant image, which I will show you in a shorter time. I think next we have, yeah, right. So here if you see on the right side and the bottom, the disease leaf there are two types of disease leaf. One having the bottom of the leaf has almost 50% of the area covered with green, but the rest part is diseased. Very good for a model to find it out. But if you look at the top right, the disease leaf image, the entire leaf is green, the background is also similar, and then it has very tiny spots with brown spots, and that is a disease. And then for the model it becomes very difficult until and unless you give it thousands and millions of images. So it becomes very difficult for the model to identify whether the disease is present in the leaf or not. And then that's where the problem starts, because if you look at a healthy image, it's very same as a diseased except the brown spot. So you will say that's what the job of CNN is, right? To predict and to figure out the complex patterns in it. But the problem is we don't have the amount of data that we want, that the model needs for generalization. So in those cases in the real scenarios, the accuracy drops, the misdiagnosis happens, and then there's a very big problem. I'll tell you one more, which I did not write in the problem statement, but that is misdiagnosis. Meaning, let's say you go to a doctor, you tell doctor you give the doctor some symptoms. Doctor, instead of telling you have a fever, tells you have a stomach ache and gives you medicine for stomach ache. Then that's a misdiagnosis, and that will harm you, or may even go ahead and kill you, right? So same thing happens with the plants. Misdiagnosis is a bigger problem than actually telling what the disease is. So that kind of making the model more robust, more generalized, having more complex pattern, having the ability to look at the complex or the critical patterns as we saw here, is what we are trying to address over here. Now how we are going to do it? We are going to do it with the help of attention mechanism. And why? Because attention mechanism helps you to focus on different parts of an image. And the way those mechanisms work is we divide the images into several patches, give the patches the mechanism, whichever attention mechanism we are utilizing, that should look at the images and point out. Now how it does is, it doesn't do it automatically, but at each run it gives the queries and the key some values, and based upon that stuff happens. Based upon that the training happens in several iterations. In the several iterations it gives a probability score to each and every patch, and then tries to figure out whether the let's say in the first run it gave a score of to the healthy part more, but the disease part was less, and then it figured out no, this was a disease leaf, right? So in the next iteration it's going to update that. So in a very similar fashion the attention mechanisms work. It helps you to focus your attention, basically attention, on the specific or the needed part of the image which is more dominant, rather than focusing its attention on the healthier part of the leaf image. So that's what the entire problem statement was, and my approach to the problem statement. And then eventually I came up with a recursive additive attention mechanism approach. Now you can tell you have self attention mechanism, multi-head, why did you not use it? Those are complex patterns. Those are complex mechanisms. They cannot be used straightforward. There is separate method to do that. And then although I know that works, that works better than this mechanism, but at the time of when I was experimenting, I did not look at that. And then this recursive approach for additive, or recursive approach for self attention mechanism works very well. So going ahead, uh, so my proposed work, basically I proposed an encoder only architecture which uses the recursive attention layer which is there in the red part of it, and then it uses the residual blocks. Now you will tell me what these residual blocks are. I mean, if you know ResNets, you will tell me, okay, these are the ones which use skip connections. And why it does it? That's because it solves the problem of vanishing gradient, because if you pass an image, it goes through several layers, it fine tunes the I mean, basically it reduces the spatial feature vector over there. With the help of skip connection, you give it another chance, another set of features along with the already refined set of features it has, and then it gives a and then basically it reduces the problem of vanishing. I mean, I have to dig in more detail in mathematical way to understand. You can't just look at an image and understand vanishing gradient. So we'll talk about in some other video. If you want, do comment and do let me know what do you want me to do, right? So my proposed work primarily revolved around using an encoder architecture which uses the recursive additive attention mechanism to the core. Now if you look at the recursive additive attention layer, this layer was implemented by me in Python. I have a Kaggle code which I will put in the description as well. And there is a mathematical touch to it which I will show you in the next part. I mean, the recursive additive mechanism, I mean RA mechanism, basically aims at finding the complex patterns and at the same time focusing the model's attention or the architecture's attention to the important parts of the image, rather than just focusing on the image as a whole. So that makes the model more robust, that makes the model better in predictions with, I mean, general, it's more generalized. And then we also tested it with some real world scenarios where it was working quite very well. So going ahead, this is the encoder architecture which uses concept of skip connections introduced or made famous by the residual neural network, which solves the problem of vanishing or exploding gradients. And this is basically designed to maximize the feature extraction from the input images, and to solve the problem that the model is not focusing its attention to the important parts. With very limited data, we can use this architecture and get some very good results. Not just accuracy, but then misdiagnosis should also not happen, is one thing which I spoke about. Going forward, this is the mathematical touch or the core of the recursive additive attention mechanism. So first which you see is the input that we pass to the layer. Then the context vector is what, I mean, those of you who know NLP, they might be able to correlate. Those who are not, we are going to talk more about this in the videos. You can talk, I mean, you can put your thoughts in the comments, we can discuss more. So context vector is being calculated with the help of this formula, which is summation of alpha I xi, and alpha I is the attention width. Attention width is calculated with the help of the attention mechanisms. What do you say, the different attention mechanism which you use. Based upon that, it calculates. Now in case of me, the attention weights, alpha I is basically nothing but utilizes the alignment score. Alignment score is calculated with the help of the attention mechanisms formula that you have. Formula basically the mathematical equation representing that. Now V transpose tan x wi xi, I mean this equation 3 which you see represents additive attention mechanism. What's best in this is the additive mechanism is different in comparison to the other standard mechanisms before this. When it came was the W1 W2 weights which you see, those are being updated in this equation or in this, I mean eventually in the implementation of the code or in the implementation of this mechanism mathematically over a period of time. I mean what do you say, not mathematic, I mean not periodically, but with each iteration these weights are being updated. Whereas in the other attention mechanisms, the weight was fixed before starting, but then in case of this, weight is not fixed beforehand, but it gets changed or it gets updated with each run, or these are updated by the neural network. So these weights are updated by the networks that we use or the neural networks that we see. I mean, let me correct myself, the W1 W2 are being updated by the neural networks, whereas in the other mechanisms like the dot attention mechanism and the scalable attention mechanisms, those cases these are updated mathematically, but here it's being updated by the neural network eventually. So that forms the crux of the what do you say, the RAA mechanism, the recursive additive attention mechanism. And the best part is this is all being done recursively, meaning if you look at equation 5, we are passing the same, I mean the context vector along with the input to the next iteration, meaning we are going to recursively apply the attention mechanism multiple times. And how we determine that? We determine that experimentally. Like for me, we had to do this recursive approach 3 times. What it does in the 3 times or 5 times or whatever the number comes for you is, in 3 times basically it fine tunes the what do you say, the features that you have extracted. And by fine tuning, what I mean is, in first iteration it might have just looked at the healthier part of the image. Second iteration it might look at what do you say, it might look at the again the healthier part, or it might again look at, I mean there's a probability, right? It can look or it cannot look. So in each iteration we try, what we try to do is, in the 3 iterations we try to fine tune, or we try to what do you say, fine tune the feature vector that we have. Basically the feature extraction part of the classification models is the core of the model, and then at that part we apply this to fine tune the feature vector more and more, so that the model, I mean so the architecture focuses more on the critical parts rather than just paying attention to the greener part, as we saw in this image where we see there is a lot of healthy image around the, I mean the leaves. Okay, so that is it for the RA mechanism. And then going forward we apply the layer normalization. Why we do it? Because this makes sure the distribution is, I mean the what do you say, normalized. And the second thing is, layer normalization is applied to a layer, whereas batch normalization is applied to a batch. We wanted to keep it in such a way that the layer normalization is being applied to the what do you say, the recursive layer. I mean they are inside the attention mechanism. I can show you the or maybe in the next video I'll show you the implementation of this, and then we are going to understand more. So I mean this is the mathematical crux of it, and then that's what I was talking about. In such good conferences you have to be mathematically sound with these equations. You can ask me why tan h is here. Tan h introduces non-linearity. If you don't use tan h, I mean that there is a domain range and all that stuff, so we can talk about that in another video. But then there is a reason why tan h is used, there's a reason why v transpose is used. So there is a reason to each and every equation. You have to understand each and every part of it. Then you are going to say, I mean then you are going to understand the attention mechanisms and the basically deep learning to the core of deep learning, which is the mathematics, statistics and probability. And okay, that's the attention mechanism. What next do we have? Okay, let me show you. Okay, now going ahead with the dataset and the experimental setup. So in that what we have is, like we took the plant village dataset comprising of 40,000 images and then belonging to 38 categories. We took this, we trained it on, I mean I trained it on Kaggle, and then eventually I also trained it on my desktop having 3060 RTX 3060. I usually train it on my local, but then I do it on Kaggle. Like I train it, save it, and put it on Kaggle, and then retrain it for some few more iterations. Now going to evaluation metrics. Now how do we evaluate the model? I told you the main problem, one of the problem statements that I told you was misdiagnosis. So basically how the models, in case of models, how we look at is, the model should be very good in the predictions. Basically it should not misdiagnose anything. So how do we ensure those stuff? Making an architecture is okay, but then how do we ensure the architecture is good? We use some metrics. I did not use metrics like MCC over here, and there are some others which we can use, but then for the sake of article I just kept it to few scores. So Cohen-Kappa and log loss are two very important scores, because Cohen-Kappa score, what it tells is, let's say you have a model, you have two models, you train them. What is, I mean it can happen that your model is just good by chance, meaning in case of an imbalanced data set, in case of scenario which I was telling you, like in case of plant disease detection, we see, right, that in many cases the plant I mean the data set is imbalanced, which is often said by many authors in many of their articles. So Cohen-Kappa score, what it does is, it tells you that let's say you took 10 sample out of your entire data set. It can happen the model is biased towards, or it's biased more towards a particular major category. I mean a category which is having majority number of images, and the minority number of I mean the one which is lesser is kind of overlooked. So if you take 10 sample out of the images, it can happen that out of 10 you have very good number of, let's say 8, 9, 5, 6 images belonging to that category, and it will be able to predict that, right? But then what about the others which are not? Because it's a minority, it's going to wrongly predict them, right? So in that case also the prediction will be very great. I mean, the accuracy will be very high, but the problem is it has overlooked a certain category which is minority, or what do you say, it just biased towards one set of images, right? Or one set of disease, what you can say. So in those cases we use the Cohen-Kappa score. It ranges from 0 to 1. The more it is towards 1, the model is very good in its prediction. I mean, between the predicted label and between the actual labels there should not be real difference, and the lesser, I mean the closer to 1 it is, the better the model is with, I mean statistically the better the model is in predictions. Basically these scores are used in cases where we have imbalanced data sets, and to tell how confident your model is in predictions and how accurate it is. Coming to log loss, now log loss tells basically, let's say you took an image belonging to X disease, but the disease was predicted as Y. Now the score for Y would be less than, I mean very close to being, I mean it could be very different from I mean very far away from 1, or it could be very close to 1. I mean basically the reason, I mean what I'm trying to tell you is the penalty or the difference between the two actual labels and the predicted labels is this log loss penalizes the model on those difference of the score, meaning the farther the score is from your real score, it is going to penalize more, and the closer it is to the real value, it is going to penalize less. So the lesser the log loss is, the better is your model in, I mean the more confident your model is in its predictions. Now what it implicates, this Cohen-Kappa and log loss basically tells is the model which we have trained is not just accurate, it also is fairly, I mean it also is not biased towards one disease. Then in the second place, it is also confident in its predictions. So I mean that's the important of taking evaluation metrics, and obviously we always take accuracy, precision, recall and F1 score as a set of metrics, and then focus is more on accuracy and F1 score and Cohen-Kappa and log loss than precision, recall. But then yeah, the combination of this works. We have some more scores like MCC, and there are a few other metrics which we use, but then for the sake of simplicity for this paper, it's not a journal article, it's a conference article, so I reduced it to those scores. Going forward, and then the work was compared with some existing works, wherein our work lies in over here, the proposed work, which you can see is very, I mean it outperforms some of the existing VIT works, because these are the latest state of the art work that has been done in the plant disease detection, and is also very much comparable with the pre-trained VITs. It is slightly less, the reason being, and the F1 score is although very much comparable, it's in terms of accuracy it's slightly less because VITs are trained on a very larger data set. They have more generalizations, right? They and our approach and our proposed work is being trained on a very smaller number of images, having a lot of issues. I mean having less image variability, having less data set, having imbalanced data set. So in those cases what I can say is it's comparable, but yes, it's okay in term, and it's also good in terms of F1 score. And F1 score is also very critical metric because it tells you the real scenario wherein, I mean the model cannot just be good at accuracy, it has to be good at the F1 score as well. I mean eventually in case of Cohen-Kappa, the model has a very high level of agreement basically between the predicted and the actual label. Basically it's telling you the model is not only good by chance, it's actually good, meaning it's not biased towards a particular set of images, a particular set of class of images, or a particular class. So that is one thing. And then for the log loss, the lower the log loss is, the model is very much confident in its and accurate as well in its predictions. So that is the comparison of the work, which you can see the model has achieved some great work. And then this also falls an important piece of experimental results in the paper, and the same works. And then this is the confusion matrix. So I could not show the entire matrix for the 38 classes, so I just showed you the first 5 for the first 5, the confusion matrix for the top 5 classes. If you see in the plant village, this is the first 5 set of images that you're going to get, class of images. So I took it for that. And then if you see, we have very few outliers, some very few like here and here. I mean, uh, that this highlights that the results are really okay, really good on a test data set. And then going ahead with the accuracy and the loss curves, if you can see, the model converges well, although it had a few hiccups in the beginning, but then that's okay. It converged eventually after some epochs. And yeah, that concludes the work basically. And the model achieved some very good results. So that's how we present an article basically, making it mathematically more sound, making improving mathematically what we have done, proving our work with some experimental results. I keep on looking at these kind of works. You also should look at more in depth to the attention mechanisms, not attention mechanisms, but then when you say deep learning, when you say NLP, when you say Gen AI, when you say chat GPTs, eventually attention mechanism forms a core part of it. So knowing them internally gives you an edge over the common set of people that you will come across in discussions basically. So that's all in this video. Eventually I will be ending the video over here. It was a long video, long talk. In the upcoming videos we are going to talk more about the conference, more about the work, more about plant disease detection, more about what's happening in the real world in this situation, more about uh, tech in the channel, more about curiosity, solving your curiosity. So don't forget to like, share and subscribe the channel. This is your friend Shubham over here. And comment करके बताओ, how do you like, do you, I mean, which topic you like me to cover. I mean, I generally cover more on, I generally work more on work. I mean, I in my organization as well, I have worked for a few cases for I mean, solved a few problems around image classification for a few clients. So that's the best part. You work here, you focus your work on these kind of topics as well. It gives you what do you say, I mean, eventually the work that's happening in the world is also revolving around data science. And also, yeah, statistics, probability, then going to the core mathematics of the equations, mathematics of the implementations of the any deep learning architecture, any deep learning mechanism, attention mechanisms will give you a better clarity of what actually happens in the inside. So that's it in the video. Don't forget to like, share and subscribe to the channel. This is your friend Shubham over here. This is bye.